this, for those of you who are at the first lecture, this one will be different. It's about essentially one subject, definability and undefinability in arithmetic. And actually, I started thinking about it. This is a major topic in model theory. This is sort of like core of modern model theory, and the trends in model theory and logic have changed much from 1950s and 60s in the origin, formalization of mathematics, in set theory, and then investigations of various formal theories were really about provability and proof systems and decidability of theories, completeness, incompleteness theorems. But slowly, with the development of model theory of various the parts of mathematics, model theory of algebra, model theory of analysis, model theory of arithmetic as well, the emphasis shifted a little bit to various classification problems. And in those classification problems, definability of concepts, definability of specific functions and relations on first order structures became a central issue. So I was lecturing about this 2 years ago. Actually, I gave a course for philosophers about the philosophy of model theory. And it turns out that there is not really that much written about it that I could recommend to students. So this talk is a summary of certain things that I find interesting, but it's very hard to give one source of reference for all those results that I will mention. I include them. And after the lecture, if anyone's interested, I have a paper written about it that has a full reference list, and also so I will be happy to send it to anyone who's interested. But also, if you have any questions during the lecture, please interrupt me and ask, because it's always helpful for the speaker to know that someone's listening. Anyway, so I will start sharing my screen in full window. Okay, is it okay now?
Yes.
All right. So let's move on. So look, so this is really just to make sure that everyone's on the same page. I assume that you know all those basic definitions. This is really introduction to mathematical logic, but just to be precise, what I mean by a definable relation or a function on a given first order structure. So this is simply not a subset, but the important things that we talk about subsets of arbitrary Cartesian powers of the domain of the model, not just the domain of the model itself, but the m squared, m cubed, and so on. So I refer to them as higher dimensional definable sets. And a set is definable. By definability, I will mean definability with parameters. So this is definability not in a theory, but over a structure. And a set is definable if there is some formula that defines it. So if there is a formula of the language of the structure with those given parameters that sort of describes exactly the set of elements or tuples or triples, pairs of elements that have the given property that's defined by this formula phi. And the collection of all the definable sets I would refer to as DEF of M. And the importance of this is, well, on one hand, this is all about definability in first order logic. And why do we use first order logic and not some other logic? Well, first of all, it's very natural. It has all the standard Boolean connectives, and or not, and then it has quantification. But when we talk about those multi-dimensional sets, it is important that crucial turn out to be existential quantification when you have a formula with a larger number of free variables. And then you quantify. Say, if I quantify the first one, if I say instead of phi and all of that follows, I would say there exists x1 such that the rest holds. Then you eliminate one free variable. So the set that's defined by this new formula is one dimension lower. And it's a projection. It's a projection of the set defined by phi onto all those other coordinates, x2, x2, xn. So quantifying, existential quantification corresponds to this important operation in geometry of projecting from higher dimensions to lower dimensions. So definable sets that form naturally a very well-defined mathematical class of subsets of a structure. For each dimension, those sets form a Boolean algebra. It's closed under unions, intersections, and complements. Then we have operations taking you from lower dimensions to higher dimensions, Cartesian products, and this is by combining formulas with different sets of free variables. And then you have projections. You have projections from higher dimensions to lower dimensions. So these are natural operations on sets of subsets of a given domain, and that's sort of it's the first step towards applications of model theory in disciplines like algebraic geometry or analysis. Okay, so an example, and I have the title of this slide here is that one could say that to know a structure, what we do in model theory, we classify structures up to isomorphism, and you want to know, have a description of the structure of a given structure, the intended structure, but also we want to classify theories in classes, naturally defined classes of mathematical structure. And the important key to knowing a structure is to know what are the definable sets in it. And so this can be, it's a vast topic on its own, but at the bottom, it's not really the bottom. Those are the important cases, are structures that are minimal, right? And the structures are minimal. If here I'm talking about definability just of the domain, a structure is minimal if what you can define only finite and cofinite sets. Finite and cofinite sets are always definable with parameters. You can say that a set is the set of B1 to Bn. You can say, oh, for every x is either B1 or B2 or B3 or Bn. All those finite sets are definable. So using negation, all the complements of finite sets or cofinite set are definable. And the structure is minimal if you cannot define anything else, just the definable sets. Now, I do the same thing as in ordered structures, in infinite order structures, they are almost never minimal, because if you take an element such that on both sides of that element, the set is infinite, so there are infinitely many elements smaller than the one that you chose, and infinitely many elements larger than the one you chose, that the structure cannot be minimal, because the set defined by the formula x is less than a, this selected element, is neither finite nor cofinite. But then there is the notion of O-minimality from order minimality. In ordered structures, you always define intervals, open intervals and closed intervals and points, and a structure is O-minimal if every definable set of the domain is the union of a finite set of open intervals and points. And those are important classes. So those are classes where you sort of have the best understanding of the structure of the definable sets. So here are important examples. And the most important example for me today is the first one, as you will see. This is the simplest structure you can think of. So these are the natural numbers with the relation of the successor. It doesn't even have to be a function, it's a relation, and m is related to n if n is the successor of n. So notice that the relation is defined externally, because the only relation of the structure is the successor relation. And then we have a slightly more complex structure, but very close to it, natural numbers with the usual ordering. And I will sort of tell you a little bit about how you prove that both these structures are minimal. And then there's a very important example, complex numbers, the algebraically closed field, algebraically closed extension of the real numbers is also minimal. But then the proof for that is uses fundamental theorem of algebra and other things in algebra, but it makes this whole idea of minimality an important, that classical mathematical structures, some of them are minimal, some are not. Okay, when you go to ordered structures, it's not difficult to show that the integers, z stands for integers, right? Unlike the natural numbers, the integers are not minimal, they cannot be minimal, but they are order minimal or minimal. And so is every densely ordered set. So the rationals with the ordering are minimal, the reals with the ordering are minimal, and so the ordering on densely ordered sets is those are examples of order minimal structures. Now, if you add more structure to it, you look at my third example here. Those are the rationals with addition and the ordering. So this is an ordered divisible abelian group. It turns out the proof is harder, but not very difficult. So these structures are also order minimal. The only sets of rational numbers you can define in the language with plus and the ordering are the finite unions of intervals and points. Now, I didn't include the situation, what happens when you add addition. When you add addition, everything changes completely. It becomes a very, very unclassifiable structure. You can define integers, you can define all kinds of things. This is very close to the standard model of arithmetic. But now if you go to the completion of the rational numbers, topological completion, you go to the real closed field with addition and multiplication. This is a theorem of Alfred Tarski, that this structure, which is richer because it has a larger domain, it's also a little poorer because it is actually all minimal. There is nothing much you can define. You can only define open intervals and Boolean combinations of open intervals. And it was a question of Tarski that he asked in the 1940s. What happens if you enrich the structure? What happens if you expand the real closed field by adding the exponential function or the graph of the exponential function? And it turned out to be a very difficult question that was only answered in 1999 by Alex Wilkie. And it's a fantastic theorem that shows that this structure is also all minimal. And there is a whole discipline now of studying where people study various expansions of the real closed field and with the respect of minimality and order minimality. Okay, but now when we go back to the simpler structure, the additive structure of the natural numbers, this is my example 5, and the additive structure of the integers, they are not all minimal. And if you look at this first formula here, phi of x, okay, it defines the even numbers. So even numbers are neither, there are union, is a discrete, infinite discrete set. If a structure has a infinite discrete set, if the domain has a discrete infinite definable set, it cannot be all minimal. So these are the examples, and for example, this simple reason, even numbers are definable. And notice here one thing, that here I talk about all minimality. All minimality applies to ordered structures. I did not include the ordering in the language because I don't have to, because this structure is linearly ordered by a definable relation. You can define the ordering of the natural numbers in this very simple way. X is less than y, well, if they are different, and if there is some z such that x plus z equals y. Okay, and you can easily see that it defines exactly the ordering of the natural numbers, but it is important that this formula doesn't define anything it defines the whole set of integers in this structure because you have negative numbers. When you have this quantifier, there exists z. If you allow to use negative numbers, then this formula just defines the nothing, really, the complete square, z squared. The two numbers are related. So here, to indicate that they are considering this as an ordered structure, I add the ordering to the language. And there is a difference between model theory of just z groups, just with the ordering, just with the addition function or relation, and the theory of the ordered integers. Okay, and ordering is important, and it will play a big role. Okay, look, so here I have an argument, a model theoretic argument to convince you that the ordering is not definable in the simplest structure you can think of. This is really a directed graph, countable directed graph. There is one element, 0, and then it points at 1, 1 points at 2, 2 points at 3, and so on. So these are the natural numbers with the successor relation. So So this is an argument that shows that in this structure, I cannot define the ordering, because suppose you could, okay? Suppose that there is some formula of this language that exactly defines the ordering. And then you use a little bit of model theory. You take an elementary extension. Okay, and this is, again, I understand some of you are students who just had an introductory course in model theory. This is a good exercise to see, what happens if you take a proper elementary extension of this simple structure? What do we know about it? Now, we know that they have to have to some non-standard elements, like here I have this A and B. But now what's true in this the structure of the natural numbers, that there is a unique least element, but every number that's not the least one has both a successor and a predecessor. And this is expressed in the language of this structure. So the same must be true in every elementary extension. So if you go to this non-standard part of the model, every element has a successor and every element has a predecessor. So with every non-standard element comes what I call the whole Z chain. I call it Z of A. Okay, you can keep adding, taking successors of A in the positive direction, taking predecessors of A. So those elements have to be present. Now, for the argument, I need at least two Z chains. But so you can ask, how do I know that I have two Z chains? Well, I don't have to. There are elementary extensions just with one chain. But if you apply the compactness theorem again to this extension with one chain, you can get extension with more chains. You can get any number of chains that you want. Is there a question? Right. So let's go back, because I would like you to understand this argument, because it's a simple argument. It's a model theoretic argument about definability, the simple proof of undefinability. So just to, okay, so what we're doing here, we're working over the structure with the successor relation. We assume that the successor relation is definable. Now I was talking about why an element, I can take an elementary extension. So these are the natural numbers, and this is the extension. These are the non-standard numbers here. And each non-standard number comes with a chain of predecessors and successors. And for the argument, I need at least two. So by compactness, you can get that easily. So now once you have a situation like this, what happens? So I claim that this is something that holds in the standard model, because theta is defining the ordering. So if I take any two different numbers, then either x is less than y or y is less than x, but they cannot be both. Okay? So there is a simple fact that expressible in the language of the successor relation. So because this is an elementary extension, the same must be true in this non-standard model. But this allows me to do the following thing, that I can define the function from the domain of the structure to the domain. I just move this whole block, the Z chain of A, onto the Z chain of B, and I permute those two Z chains. I send A to B and B to A, and every successor and every predecessor of A to the corresponding successor and predecessor of B, and the same here. So I'm swapping, I'm exchanging A and B with the whole Z chains. And this operation, and the function is identity elsewhere. So this operation preserves the successor relation. The successor relation hasn't changed. But, suppose that, here for every two elements, either this holds or this holds. So I have either theta of AB or theta of BA. So suppose theta of AB holds, but then F is an automorphism of the structure. So this is what automorphisms do. They take tuples of elements to tuples of elements realizing the same type, having the same first order properties. But f of A is B and f of B is A. So I have both theta of AB and theta of BA, and that's a contradiction because that's not allowed. Okay, so notice that here I proved not only that the standard ordering is not definable, but any ordering. I cannot define any ordering just using the successor relation. Successor relation doesn't have an idea about how elements of the model are ordered. And I like this argument very much because it uses, this is an example of how automorphisms are heavily used in studying definability questions. And it is applied to this structure, natural numbers with the successor, but this is a rigid structure. it doesn't have any automorphisms. I cannot use automorphism directly to study the successor relation because it's rigid. Every automorphism has to carry 0 to 0, and then has to carry 1 to 1, and 2 to 2. The only automorphism is identity. But this is thanks to compactness, thanks to, and I don't even need the compactness theorem. This is really overkill. I can construct these, a structure like this, and then prove that I can define the structure with those Z chains, any number of Z chains, and I can prove that this is an elementary extension. This requires some doing. This is not such a very straightforward thing to do, but it can be done. Okay, so this is the first undefinability result. Ordering is not definable from the successor relation. Look, but now here is one of the themes that I want to bring up. Everyone knows that the ordering of the successor relation on the natural numbers already determines everything. It determines addition, it determines multiplication, and much more. If this is the beginning of computer science, okay, that you can do addition and multiplication and all kind of other computable functions recursively. Okay, so this is a definition of addition, recursive definition. Okay, x plus 0 is x, and x plus the successor of y is the successor of x plus y. And here we assume that we know already what the successor of x plus y is. And similarly, you can define multiplication, and you can define much, much more. So, so this is really a little bit of a scandal that the successor relation already determines so much about the structure of the natural numbers. Okay. Anything sort of is uniquely determined by the successor. Addition is, multiplication is, and then if you studied arithmetic and the definability power of the language with addition and multiplication, you can define everything else. And that is because, but for all of that, you have to use recursive definitions. So what's the lesson here? The lesson here is that first of all, the logic, well, is good for many, many things, but the fact is that it cannot capture recursion. It's not, the recursive definitions cannot be converted in a straightforward way to first order definitions. If you studied the model theory of arithmetic a little bit, you know that it can. Recursive definitions can be converted to first order definitions over Peano arithmetic. Peano arithmetic is strong enough, but that uses this whole power of coding Gödel's beta function and all kinds of things to be able to do that. This is the essence of Gödel's arguments about arithmetization of the language. It's a complicated machinery, but for simpler structure, first order logic is very weak. It cannot define things that are otherwise easily definable in other ways. Look, so as I said, why the recursion works in this structure, this ordered set, because it is well ordered. That we know that every element, every natural number can be reached by iterating the successor relation. So this is true in the standard model. It is definitely not true in any non-standard model. You cannot reach A nor B by the successor relation. The iterating successor relation gets you only as far as the natural numbers. You cannot reach the non-standard part by iterating things simply. Okay, so this is all those non-standard models that are not well ordered. So this sort of uniqueness of determination does no longer hold. So here are the kind of questions that we'll be looking at. So now look, so we know that the successor, if I now take a model of the theory of the ordering of the natural numbers. So in this model, I defined, you easily define the successor and predecessor relation because it's a discrete ordering, so it defines successor. So the successor relation is definable in any non-standard model of the theory of the standard structure. But the question is now, but does this successor relation determine the ordering? We just saw a moment ago that it doesn't. But it doesn't in a first order way, which means there is no first order definition that gets you from the successor to the ordering. But maybe in somehow the successor determines the ordering in some other way. Okay, but then we can continue. So now we go a richer structure. We have seen that if you take a model of the additive structure of the natural numbers, then you can define the ordering easily in this structure. But Does this ordering determine, in any sense, the addition? Can there be models with the same ordering and different additions on it? And then it continues. So now we go to a larger structure. Now we have the additive structure and add multiplication to it. So here, for some reason, I use theories of these standard structures because the theory of the ordering is axiomatizable easily. That's an exercise in model theory. The theory of the additive structure of the natural numbers is axiomatizable. This is Pressburger arithmetic, axioms of Pressburger arithmetic, infinite set of axioms, but this is a complete axiomatizable theory. When you go higher up, things are no longer that easy to discuss. So we're not talking about the theory, the true arithmetic, the theory of the standard model, but some axiomatic theories of it. So the question is, if you are in some model of some axiomatic number theory, like Peano arithmetic, and you already know your addition, does it in any sense determine the multiplication in a similar way as it does in the standard model? Everyone knows, you learn in school, maybe first or second grade, that multiplication is just repeated addition. Addition completely determines multiplication of the natural numbers. But what happens in those non-standard models? And the interest here is by finding out not what happens in a particular model, but what does the theory have to say about the connection between addition and multiplication and vice versa? Suppose you know your multiplication. Do you know anything about the addition? And similar questions. Do you have any questions? Okay, I have. So these are my questions. So, but to discuss it, we have to talk a little bit about this general model theoretic concept of expansions. So this is what we're doing here. We have a structure with some functions and some relations on it. We're adding additional relations and additional functions. So this is called expanding. You expand the structure and usually you do it. Okay, you have some new relation symbol, and you expand this structure of a given theory T to some theory that says something about connections between what the functions and relations of T, how are they related to this new relation that I'm introducing. So this is really what I have been talking about, just a moment ago on the previous slide. So we have models of the theory of the successor, and we want to see something about their expansions to models of the ordering. We want to order them to an ordering which satisfies the theory of the natural numbers. But okay, so we go one step up. Then the next step up would be from the ordering to the additive structure. So you want to have the ordering that looks like the ordering of the natural numbers, and you want to add addition to it so that what you get looks like the natural numbers. So it is a model of Pressburger arithmetic. I just mentioned this. Pressburger arithmetic is the axiomatization of the additive structure of the natural numbers. But then we can continue. We get a model of Pressburger, and we ask, okay, so can I expand it to a model of full arithmetic? Can I add multiplication to addition such that what I obtain is a model of Peano arithmetic? And then we can continue. This is something that I mentioned last week, this sort of Tarski's undefinability of truth. You have a model of PA, and there are now these days what's really heavily studied is various axiomatic theories of truth or satisfaction of a model. How can I expand a non-standard model to a model of some axiomatic theory of truth? And the point is that you have a non-standard model of axiomatic theory of truth, that the theory talks not only about standard sentences and formulas, but it talks about sentences and formulas of the model, which can be non-standard elements of the model, non-standard Gödel numbers. Okay, so this is the program. This is the kind of questions that we'll be looking at. Okay, so this is so now before we do that, let's see what's happening in the standard model. So we already talked about it. I showed you the proof that the ordering is not definable. So because of that, this is a proper extension. Okay, and again, I'm saying this is an extension. You don't see the successor relation listed here because I don't have to list it because it's definable. The successor is already visible. I call it logical visibility. the ordering knows its successor relation. So I don't have to include the symbol for successor relation here. Okay, but now, because even numbers are definable, and I told you that this is a minimal structure, and plus the additive structure is not minimal, then again the additive structure is a proper extension. There are some new definable sets in the richer structure that were not definable in it. So in particular, so addition is not definable just from the ordering. But now, if you want to go higher up, there are many ways in which you can argue, and you can think of some other that show that multiplication is not definable from addition. This follows from many classical results. For example, it follows from undecidability results about Peano arithmetic. But there's a beautiful theorem from 1960s by Ginsburg and Spanier, and who completely characterized subsets of the natural numbers that are definable in the additive structure. Every such set must be what's called ultimately periodic. So what it means that the initial segment of this set X, we talk about definability with parameters, so we can define any finite set. So the beginning of a set can be anything you can think of. That can be some fluff. But the theorem says that the structure of the definable set cannot be chaotic forever for sufficiently large L. So if you go high up, there must be some P such that the set becomes periodic. If X is in X, then X plus P is in X. It becomes kind of a very stable set after that. It repeats itself. Okay, so for example, squares or prime numbers, have simple definitions in the multiplicative structure, but they are not ultimately periodic. Neither squares nor primes have this property. They are never periodic. So they cannot be defined in the additive structure, so multiplication cannot be defined from addition. So again, this is this sort of evidence of weakness of first-order logic. Recursively, you define multiplication from addition simply, and it works in the standard model. This definition will not work in non-standard models because it really uses the fact that the standard model is well ordered. Non-standard models are not, and those definitions by recursion do not work there. Okay, and this is like a digression. It's interesting, the structure of definable sets in the multiplicative structure is more complex, because the structure is more complex, but there is a very simple argument that shows that you cannot even define the successor relation. And you cannot define the successor relation from multiplication because there is an automorphism that takes 2 to 3 and 3 to 2. And actually, you can take any prime number and move it to any prime number. The way you do it, you take prime decomposition of any number, and you replace every occurrence of 2 with 3 and every occurrence of 3 with 2. And then you show that what you get is actually an automorphism of the multiplicative structure. So now, if you have an automorphism like that, if you have a function that permutes two elements, you cannot define. It's okay. So you cannot define the successor because this automorphism will have to preserve the successor relation, but it doesn't. Okay? It moves 2 to 3 and 3 to 2. But it's an interesting fact that the fact that that this is the only obstacle. If you have access to the successor relation, then you can define addition in this structure with multiplication and the successor function. But this is slightly non-trivial. I found it it's well known. It has been known for ages, but I found it in this very nice paper of Said Salehi on axiomatic and non-axiomatic mathematics. And this is something that he calls Tarski-Robinson identity. So on this side, this is the relation of addition. X plus y, X and y and z are related by addition. And this condition is a nice exercise in high school algebra to show that this holds if and only this holds. But this formula here, this equation, is expressed in the language of multiplication and the successor only. So this is, you have addition defined from multiplication and successor. So actually, this is actually good to know. You can do this exercise at home. It's a nice exercise. All right, look, but now going higher up. So this is what I talked about last week, and I showed you a proof, a model theoretic proof, Robinson's proof of Tarski's undefinability of truth. There was a question then, why am I using binary satisfaction rather than unary truth? This can be done both ways. I use binary satisfaction. Binary means you have a set that is composed of pairs of a Gödel number of a formula and an element of the structure that satisfies the formula. This can be all done in unary truth predicates when you have numerals for every element of your structure. But the proof that I showed you was just simpler in notation in this binary approach. Those are interchangeable. And so that's another step. You have a set that you exactly know the meaning of what's written here. This is by Tarski's definition of truth, but this turns out that this structure is undefinable in the standard model. It's not arithmetic. So this quite often is presented as some kind of, some mystery about satisfaction or truth. Truth is undefinable. We do not have the access to truth. We do. We know exactly what this means. And the only thing that first order logic in the language with plus and times is not strong enough to express what we know. And how come we know exactly what satisfaction is? Look, this is an old result that was already known to Kleene and Church, 1940s, that you can define uniformly satisfaction relation if you know in advance the quantifier complexity of your formulas. So for every n, the satisfaction relation for formulas of a given complexity is definable. So it's really not a problem. Truth, in a sense, is definable, except each definition is different. The theorem here says, Tarski's theorem says that there is no way to somehow take those infinitely many definitions of partial satisfactions and combine them into a finite formula that will define total satisfaction. Okay, so that's the top of this hierarchy that I want to talk about. But now we switch gears because, okay, this was all about first order logic. So first order logic is referred to as L omega omega. You finite Boolean combinations and of formulas, and that's it. But this is the first step towards infinitary logics, when together with first order logic, you have two new operations. You can take any countable set of formulas that you already have and form their infinite conjunction and form the infinite disjunction, but with additional requirement that all the formulas in these sets must have a fixed finite set of variables. So what you get at the end is a formula, a new formula. It's infinite, but it has the fixed set finite number of free variables, and that is helpful in studying definable sets. So the definable sets in this language will be still subsets of finite Cartesian powers of the universe, of the structure. And look, and this step is also very natural from the point of view of mathematics, because in definable sets in first order logic, form Boolean algebras. They are closed under unions, intersections, and complements. And here you add the two new operations that are classical in modern mathematics, in unions and intersections of countable definable sets. So you just expand the power, but it turns out that this is already huge. So here is an example of what you can define in the natural numbers just with the successor. Well, you can define any set because, first of all, this structure becomes pointwise definable. 0 is the only element that does not have a predecessor. So phi 0 defines 0. 0 is the only element that satisfies the function. And now for every n, you say phi of n plus 1 holds if there is a y such that phi n of y, but there is only one y by induction. There is only one y that satisfies phi n, and that's n. And then we say, oh, and x is the successor of y. So this formula now defines phi n plus 1. Every number has a definition. The structure is pointwise definable. And now using this L omega 1 omega, I define X simply as the set of those X's that are in X. Okay, you just say the disjunction of the formulas where the indices come from the set X. So that's exactly X. So just by expanding this language, well, it's a vast expansion because you go to infinitary operations. You can define any set you want in the natural numbers with the successor. And because of that, you can also define, I will go over this briefly, you can define addition and multiplication by simply taking disjunctions. It's like taking unions of finite, these are countable structures. So in the countable structures, you can decompose your set into singletons. Then if you can define this is like a triple, m and k, such that m plus n is k, and you can take the union of all of that, and that's the graph of addition, and you get a graph of multiplication. And the same, you can define satisfaction. You just take the union of those partial satisfaction predicates for each complexity n. Okay, but this is sort of very straightforward and almost trivial. But also in this L omega 1 omega, these sets, addition, multiplication, they have all recursive definitions from the successor relation. And if you analyze those recursive definitions, you will see that you can easily express them in L omega 1 omega. So it's not only that you have some definitions that, there is not much difference between X in complexity as the formula here. This is really a disguised version of the set X, but there are natural definitions of addition, multiplication, and satisfaction that you can express the recursive conditions in L omega 1 omega. So you have natural definitions, fully understandable definitions that define those concepts in the basic structure. So I have been saying that the standard model of arithmetic is really the natural numbers with the successor relation, because the successor relation already determines everything. It knows already everything. You just have to move to a slightly higher logic. Okay, now, so the question is, what is the expressive power of this logic? And it's really too much. It's wonderful, and those things are being studied intensively these days. Although the theorem itself comes from 1965, that for a countable structure in a countable first-order language, for every structure like that, oh, and here there's a typo. Oh, there is a terrible typo. This should be L omega 1 omega, like here. So there is a sentence of this infinitary logic that characterizes the structure up to isomorphism. So for every structure, a countable structure in a countable language, there is some sentence such that the sentence is true about M, and any other L structure in which this sentence is true is isomorphic. And by the way, the satisfaction relation is extended to Tarski's truth definition for this L omega 1 omega. Is a very straightforward generalization of the truth. You just, in a natural way, extend these definitions of truth and satisfaction for infinite conjunctions and infinite disjunctions. Okay, so every countable structure is characterized uniquely by a single sentence of this L omega 1 omega. But my point was that we don't need this whole power of L omega 1 omega, that L omega 1 omega expresses in a natural way some very basic formal definitions in mathematics, making them completely sort of understandable. Okay, but now to get to the topic of what I call absolute undefinability, we talk a little bit about recursive saturation, and I will tell you why. This is something that I was planning to do last week, but I didn't have time. There was a whole section about recursively saturated models, so now I have to do a kind of shorter version of this introduction. Okay, in general, in model theory, saturation plays a big role. Instead of studying all structures for a given theory or for a given language, it's convenient to move to structures that are saturated in a way. And saturation means that if you have some infinite set of conditions that, some conditions with parameters from a model, they describe some property of an element. And then if this infinite set is consistent, if its infinite set can be and every finite fragment can be realized in the model, then the whole set can be realized. It means you can realize all types. Those are the types of elements of X. And there are various notions of saturation when, depending on what's the cardinality of the set of parameters you can use, and what kind of formulas you can use in the type. And the thing in general model theory is that those saturated models do not always exist. It takes set theory to construct some models of large cardinalities that have saturation properties. So for that reason, I mean, there were other reasons too. John Barwise and John Schlipf, and this was in 1970s, defined this concept of recursive saturation, that it's a saturation with respect to sets of formulas that are computable. And you consider, so this makes sense for languages that are either finite or computable languages. And if you have a computable set of formulas, then, well, there are only countably many, and it's easier to find models that are saturated with countably many of those infinitary conditions. So this is what makes a structure recursively saturated, that for any computable type and for any parameters that you stick into the type, if the type is finally realized in the model, then the type is realized. So then there are all kinds of things. There's a general theory of recursive saturation, that now every structure has an elementary extension that is recursively saturated, and it's the domain stays of the same cardinality. So every countable structure has a countable recursively saturated elementary extension. So they do exist. And they have all kinds of important properties, some universality property. There are many, many things that can be said about them, but it's even better than that. There is a related concept that's known as resplendent. Now, Jan, can I ask you, would people know what resplendence means in English?
Yeah, our students haven't learned this notion. Maybe you can explain more.
No, I will explain what it means technically, but what it means in English, it's radiant, it's extraordinary, it's fantastic, it glitters. There's a nice translations into Polish of resplendent. This is something you are at awe, you are struck by the beauty of a resplendent model. Is there a word in Chinese that could be used? How would you call resplendent models in Chinese? No,
Anyway,
extraordinary beautiful. Is there a single word for that? I'm sure there must be. Anyway, you can look it up in a dictionary. But,
okay.
but resplendent models are truly resplendent. So because this is the definition is about saturation, but not with respect to first order properties, but with respect to the second order properties. And maybe this may not be a very helpful picture, but instead of reading this, I will point to you what's happening here. So this is the idea. You have this structure M, and it's in a certain language. Okay, and now you have this new relation symbol that is not in the language of the structure, but there is some property of that relation that you describe using the properties of functions and relations of the original structure. And now if this property, this is again compactness theorem, if what this property says is consistent with the theory of the model, then there always will be some elementary extension. There always will be some larger model and some relation such that this property holds in these elementary extensions. This is just simple consistency question. If you extend the language and if it's consistent that this relation has such and such property, that you can always extend your model to a larger model that has a relation with that property. But now a model is resplendent if you can already find such a relation on the original model. So the model is saturated. Now, recursive saturation says you are saturated with respect to properties of single elements, but this is a saturation with respect to properties of relations and functions. So it's a sort of second order saturation property. And later on, it turns out that instead of phi, I can also have a whole theory of this new relation as long as it's computable. So it's really a powerful notion. It's not clear at all whether these models exist. So how is this resplendence a relevant notion? So first of all, Barrois and Schlipp showed that every countable structure has a countable elementary extension that's recursively saturated. But then there is a theorem, a beautiful theorem of Barrois and Schlipp, and independently Jean-Pierre Resser, who showed that countable recursively saturated models, the countable models are recursively saturated if and only they are resplendent. So resplendence seems like a much stronger concept than recursive saturation, and it is in general. There are recursively saturated uncountable models that are not resplendent, but for countable models, these two notions are equivalent, which is fantastic because you use recursive saturation to show that countable models that are recursively saturated exist. But then you use the theorem to say, oh, those models are actually even more than recursively saturated. They have all those fantastic properties. But now, where do these models appear in so-called nature? Where do you find them in mathematical practice? Look, so the fact is this, I call it a theorem of Pressburger, but Pressburger had no idea about this model theoretic concept. What Pressburger proved is a quantifier elimination for the additive theory of the natural numbers, and together with a decision procedure. But what follows from Pressburger's elimination of quantifiers is that in arithmetic, in full arithmetic with plus and times, there is a satisfaction relation for sentences or formulas just in the additive language. There is a definable satisfaction predicate for the additive structure of M in M plus n times. And if the model is non-standard, and it is similar to this Robinson's proof of Tarski's undefinability theorem that I showed you last time, this is sort of very similar argument that if you have a definable in arithmetic satisfaction relation for some reduct, then that reduct must be recursively saturated. Okay? So it means that in all non-standard models, the additive reduct is recursively saturated, and therefore it's also resplendent. And the same for the multiplicative structure. But for the multiplicative structure, you need, again, the sort of effective elimination of quantifiers for the additive structures. And Skolem already proved decidability of the computer of the theory, multiplicative theory of the standard model in 1930s, but in a different language, and it's not axiom without giving the complete axiomatics. So this was Patrick Segilski and Mark Nadel independently. They provided the whole axiomatic system for an elimination of quantifiers for the multiplicative structure. And again, this gives you a satisfaction relation in full arithmetic for the multiplicative reduct. So that makes the multiplicative reduct recursively saturated. And then I will, this is a kind of a separate topic, and I will not, again, this is like a large area of study. If you go one step up, remember when we're going up and up from successor to ordering, from ordering to addition, from addition to addition multiplication, and then from addition multiplication to satisfaction and truth. And this is a remarkable theorem of Kotlarski, Krajewski, and Lachlan from 1981, that if you have a countable non-standard model, it carries a full satisfaction class. And full satisfaction class, again, means this is the semantics for a non-standard model, a complete semantics for non-standard formulas of a model that obeys Tarski's satisfaction definition. A full means that it decides the truth value for every formula. Every formula or its negation is true according to this satisfaction class. And this happens on a non-standard model if and only if this model is recursively saturated. It was an important theorem, and there are many, there's much that's being done about these sort of related questions about these. So this is sort of like a starting point for those various axiomatic theories of truth. Okay, so that's so again, so this is recursive saturation comes up, and but here I said nothing about the induction that you want to be satisfied together with this new relation, satisfaction relation. But here is an example about I think this is the weakest of those axiomatic theory of truth. They use the symbols for the UTB. This is uniform Tarski biconditionals. And this is an example of this axiomatic theory of truth. This is in the language of PA. Together, this unfortunate thing, but I didn't want to change it. We have to sort of be alert now. This is no longer the successor relation, as here traditionally stands for the satisfaction relation. Okay, so here we're talking about the satisfaction relation. And here is the simple axiom schema. You just want to say that for every, so here phi is a standard formula, so it's a schema for every formula. Well, it's the truth value of this pair, the Gödel number of the formula, and y. This holds if and only if phi of y is true. So it simply says that according to the satisfaction relation, it just extends the usual satisfaction relation. But the key is that you also require that if you have a structure together with this new relation, the full induction schema holds for the language. And it turns out, so this is a very mild condition. Okay, you just want to have this satisfaction predicate extend the true standard satisfaction, but you require the induction holds in the extended language. So this theorem comes in two parts, that if you have such a satisfaction class, if your model is expandable to a model of UTB, then it must be recursively saturated. This doesn't use countability. This just uses the fact that once you have this satisfaction relation and you have induction, you have the overspill principle. Oh, I see. Well, I even, I give some hints of the proof. So here, if you have a computable type that's finitely realizable in M, then you express this finite realizability of the type in the model by the formula in the language with S, and then you have the overspill principle. So you overspill, and you have an element realizing the whole type. And it works without any assumptions on the cardinality of the model. But now, in the other direction, if M is resplendent, so in particular, if M is countable and recursively saturated, then it is expandable to a model of UTB. Because if you look at this is this theory. You have your resplendent model, and you want to expand it to this new relation that satisfies certain properties. So the properties are explicitly written here, plus you have the induction schema. But now, all you need for this this theory expressing these conditions to be finitely realizable somewhere has to be consistent with the theory of the model. But now, if you take finitely many of these conditions, then this SSS, you can take the union of the elementary diagram for these finitely many formulas phi. Okay, for every phi, you have a set defined by phi, and you take the union of those. And so this will be the truth relation for those finitely many formulas. And it's the union of definable sets, so it satisfies the induction schema automatically. So this simple argument shows that the theory, the UTB, is finitely consistent with the theory of any model. But now, if a model is resplendent, then it has an expansion. So it has this satisfaction class that satisfies these conditions. Okay, so again, this is the connection between these two concepts: recursive saturations, resplendence, and non-standard models, and truth and satisfaction. And this is I will use it later if I have time. We're talking about arithmetic, but there is more. This in model theory of these kind of arithmetic-like theories, resplendence and recursive saturation comes up often, but also in set theory. And there is a beautiful paper, actually two papers of Joel Hamkins and Makoto Kikuchi. When they look at this sort of in the 1920s and 30s, people wondered, we studied set theory, but what about something that could be called mereology? And the mereology is the theory of parts. You talk about not sets and the membership relations, but sets of objects and the primitive relation being really a subset, being one set being a part of another set. So what are the axioms for these theories? What is the strength of these theories? We know that set theories are incredibly powerful, okay, especially given the axioms of something like CFC. But what about the power of this? And this result shows that this is sort of nowhere near the. You can think of this if you have a model of a set theory, then this inclusion relation is definable in the model. So this is like a definable reduct, and you can see about what it is. And Hamke and Kikuchi showed that this model, no matter what your original countable model is, and there are continue many different models for different extensions of the FC, but they all are omega saturated. If they're omega saturated, means saturated with types, arbitrary types with finitely many parameters. So in particular, they are recursively saturated, and because of that, they are resplendent. All those reducts, no matter what models of set theory you start, all those reducts will be resplendent. And moreover, up to isomorphism, there is only one such reduct. So all those, continue many non-isomorphic models of set theory, they have the same reduct to this the inclusion relation. And conversely, if they prove that if you have a resplendent model of the theory of this unique model, that is always expandable to a model of CFC. So it's not. So I'm saying that this is not just arithmetic. It's sort of those resplendent models come up everywhere. But look, so now going back, I haven't defined absolute undefinability yet. I am just about to do it. All this was needed for an introduction, so I can talk about absolute undefinability. Look, so first, there are some preliminary results. This is the result of Scott from the same paper, when I was talking about Scott's isomorphism theorem, that every countable structure is identified up to isomorphism by a single L omega 1 omega sentence. But what follows from it, that the following conditions are equivalent. So suppose you have a certain structure, any countable structure. I guess we have to assume that the language is countable everywhere here. I didn't put it down. And you have a certain relation. So the following, just a subset of some Cartesian power of the model. The following conditions are equivalent. That suppose that the set is preserved by all automorphisms, but it's preserved setwise. The function can permute elements inside X, but the image of X is X. This is equivalent to saying that this set X must be L omega 1 omega definable without parameters. Okay? The implication from 2 to 1 is obvious. It's obvious in the sense that this is a logic, and this is what logic does. Logical properties must be preserved by automorphisms. So it doesn't really matter what this logic is, and it has that property that if you have a set that's definable in this logic without parameters, then those sets cannot be moved by automorphisms. They can be moved internally. Elements inside can permute, but the image of a set, a definable set, must be the set itself. So from 2 to 1, it's obvious, and from 1 to 2, this is the power of Scott's theorem. Okay, but now, so this is the question of definability without parameters, but David Keeker, in his PhD thesis, we're talking about 1960s, 1967, he proved the following thing, that no, because what happens when you change this definability without parameters to definability? Now, when you allow parameters and your structure has automorphisms, so automorphisms can move parameters. So if you move parameters, the whole set defined by a formula with those parameters can move as well. It does not have to move, but it can move. So this is this implication from 2 to 1 no longer holds, okay, because the parameters can be involved. But he proved the following things, that these are equivalent conditions. A relation is L omega 1 omega definable if and only if, well, this condition here says that the set has only one automorphic image, just identity. But if you have parameters in a countable structure can move to countable many other parameters. So at most, there can be at most Aleph zero automorphic images. And then by general model theory and some set theory, this turns out to be equivalent to having fewer than continuum many automorphic images. And so this really, this is the theorem that gives you some kind of handle on how to study definability, because this is a condition. How do you find out that the relation is definable? You have to look for a definition. Okay, and this might not be an obvious thing to do, but how do you prove that it's undefinable? Well, it's not that you cannot find a definition, but you look at possibly at what can be possible automorphic images of a given relation, and if you can find more automorphic images than countably many, then you know for sure that your relation is not definable in L omega 1 omega. Okay, and but in particular, look, so this says that if the automorphism, if you are in a structure, countable structure that doesn't have many automorphisms, then every relation is L omega 1 omega definable. Okay, because you cannot find continuum many automorphic images because you do not have enough automorphisms. So rigid structures are no good, and structures that have few automorphisms are no good. To sort of look at the sort of arguments involving undefinability, you have to look at that structures that have lots and lots of automorphisms. And again, this is a common theme in model theory. You really want to study structures with many automorphisms because then you can use theorems like this one to prove something about theories of those models, definability and undefinability results. So this leads to this, this is something that I defined, but it was other people looked at similar definitions earlier, but I was surprised that it wasn't really a theme in the 1960s and 70s when Kicker and other people were proving their results, that I call a relation on a countable structure, that if it's definable in some logic, okay, so this is a corollary, then it must be L omega 1 omega definable. This L omega 1 omega is really ultimate for countable structures. And because how do we know that? Because that's what I just mentioned, that if you call something a logic, this is sort of Tarski's criterion, that logical properties are preserved under automorphism of structures, or in general, isomorphism between structures. That if you have two isomorphic structures, they should have the same logical properties. So any reasonable logic must have this property. So any definable set has fewer, at most countably many automorphic images. And by the theorem of Kicker, then it follows that this relation is already L omega 1 omega definable. Okay, so it doesn't really matter what those other logics can be. L omega 1 omega suffices. So this gives me this motivation to say I call it a relational structure absolutely undefinable if it has continuum many automorphic images. And Greek logician Athanasios Tsouvaras already studied the similar notions in his paper in 1991. This was related to recursively saturated models of arithmetic, and actually he was working in. There was this what's called alternative set theory that was studied in Czech or Slovakia then, and it called so what I call absolutely undefinable, he called imaginary.
Excuse me.
Okay. And and here I just want to mention there is essentially one tool. Kicker and Reyes wrote the PhD thesis essentially at the same time with very similar ideas. And here is this model theoretic tool to sort of detecting whether a relation can have continuum many automorphic images, and it's sort of localized. It says that if for every finite, you are in a countable structure, suppose for every finite tuple, you will find, this could be tuples as well, but think about one-dimensional relation, a unary predicate, that you can find two elements, B and C, one in the relation and C not in the relation. They still have the same type. So you fix any finite fragment of the model, and you can still find two elements that look the same in the model over this finite fragment of the model. And if you can do it forever for every finite tuple, then R is absolutely undefinable. So that's a very useful lemma, because this condition is actually something that's not that difficult to work with. And so what are the theorems? What are the results? So first of all, countable resplendent models, or countable recursively saturated models. So for here is all, you can say countable recursively saturated, countable resplendent, it means the same. So they all have continuum many automorphisms, so you can sort of begin thinking about which relations on them have continuum many images and which do not. But by the theorem of Schlipp, you know that maybe I missed this on one slide. It was on the slide, but maybe I didn't talk about it. But because here I talk, the theorem of Schlipp talks about resplendent structure, but now here is an additional relation on it such that the expanded model is also resplendent. Let's see, do I have this? No. So I will just say what resplendent models are. Resplendent models are also chronically resplendent. And that's another theorem of Schlipp and Barwise. And it says that if you can expand a model M to some relation that satisfies certain conditions, either a single sentence about this new relation R or a computable theory about this new sentence R, if you can do that, that you can also expand it in such a way that the expanded structure stays resplendent. Right? Because what's resplendent from the beginning is just M, but chronic resplendent says that if you can expand, you can also expand so that you keep resplendence. You didn't destroy resplendence by adding this new relation. So this theorem says that if you have a resplendent model, and of course, if this R is definable in M, that it is, all definable sets are just part of the original structure. But if the whole pair, the model and this new relation, is still resplendent, then this R has continuum many automorphic images. Okay, so there is a theory that there is a corollary, which I call absolute undefinability cannot be avoided. That it says that if you have any property such that you can expand a resplendent model to a relation with that property, then there will be always some expansion that's absolutely undefinable. Because by chronic resplendence, if you can expand in such a way that this structure is again resplendent, and then by the theorem of Schlipp, this relation will have continuum many images, so it will be absolutely undefinable. But absolutely really means absolutely. It really means no matter how hard you try, you will not see any connection between the structure of the original model and the construction of this new relation. This new relation has absolutely nothing to do with the original structure. It is just a result of a kind of a back and forth construction or some set theoretic argument that shows that this relation exists. Because if you are absolutely undefinable, then you're not really connected to the original structure in any reasonable way. Okay, so I think that these are kind of interesting concepts, and I was surprised that they were not really studied in greater detail in the 60s and the 70s. But I guess there were many other interesting things that people did there, and this was somehow overlooked. So now we're getting sort of closer to what I really wanted to talk about, because it was supposed to be absolute undefinability in arithmetic. So we're going back to my examples from the beginning. So let's start with expansions of the successor relation to the ordering. So, and it takes a very little general model theory to see that you can take when you take a model of this, it was like on my picture at the beginning, this model consists of the standard, a model of the theory has a part that's the standard model, and then it has the union of Z chains. Okay, any number of Z chains, finitely many Z chains, the parts of the model that look like the integers with the successor relation. There could be infinitely many Z chains or finitely many. And any such model, it's easy to see that you can always expand to a model of the theory of the natural numbers. I say easy, again, because you can sort of do a complete analysis what these models look like. And by the way, for students of Professor Chang, if you are using my book, Model Theory for Beginners, so there are sections in the book that are devoted to complete analysis of these of this situation. So now look, so expansions always exist, but now but if the model is recursively saturated, all those expansions are absolutely undefinable. Using an argument like this, Kieker-Reyes lemma, and up to isomorphism, there is only one countable recursively saturated model of this theory, and this is the one that has infinitely many Z-chains. So we have complete classification of countable non-standard, actually all models of non-standard models of the theory of the successor. And for countable models, there's only one of them is recursively saturated, and that's the one that has infinitely many Z-chains. And all the others have finitely many. And if you have finitely many Z-chains, you can see exactly how many automorphisms they have. They have only countably many automorphisms. So all those expansions have to be L omega 1 omega definable, but more, you can actually see exactly what those expansions can be. There will be only finitely many up to isomorphisms, those expansions. You can see exactly what those expansions are. Okay, so this is what I said in the third part. If you have a model that's not recursively saturated, it has finitely many Z-chains, and it's easy to see that all expansions of those Z-chains to the ordering are L omega 1 omega definable. You can actually explicitly write natural definitions of those orderings. So that's the situation when you go from the successor to the ordering. Okay, so now we're going from the ordering to addition. And here the situation is harder to analyze. But again, we know from this previous, I told you there was this slide that shows that resplendents and recursive saturations are everywhere, and particular reducts to addition of models of Peano arithmetic are recursively saturated. But even if you go at this level, if you want to go from the model of the ordering to the model of Pressburger, this has to be recursively saturated already. And moreover, all those expansions, if you go from the ordering to addition, they are all absolutely undefinable. This is not a very difficult but clever argument that's due to Emil Ježabek. It is in my paper on the absolute undefinability. Emil is the Czech logician who knows everything about these questions, about Pressburger, orderings, and this is actually the model theory of Pressburger arithmetic is still far from being completely understood. There are many open questions. So this is I owe this to Emil Ježabek, this result. And so the requirement is to be expandable to a model of Pressburger. M has to be recursively saturated, and it's only one model. It is the one in you have, so this is a model of the theory. Models of the theory are composed of the standard model followed by a set of Z-chains, but now all those Z-chains are ordered in a particular type, but the model will be recursively saturated or resplendent if and only the order type of those Z-chains is the same as the order type of the rationals, dense linearly ordered set. They have to be ordered densely. So here we understand exactly what's going on. So that was the going from ordering to Pressburger. So now we're going from Pressburger to PA. And again, so this is, that's much of it is really what's called folklore, that these results were noticed by some people in various papers, but the fact that expansions exist if and only if M, the model of the additive structure, is recursively saturated, that was known long time ago and studied in different ways by various people. But the new result here is that all those expansions, when you go from the ordering to addition, are absolutely undefinable. You cannot find some special expansions to addition, especially expansions to multiplication that somehow are definable in some infinitary logic. And this was noticed by my colleagues, Alf Dolic and Simon Heller, Simon Heller was a PhD student at the Graduate Center here in New York, and he was extending some results of David Llewellyn-Jones, was a student of Richard Kay, and he studied in detail automorphisms and the theory of automorphisms of models of Pressburger arithmetic. And from some of his results, it follows that all expansions of additive structure in a recursively saturated model to multiplication is absolutely undefinable. Okay, and just last few words. I will be finishing soon. So now what about those axiomatic theories of truth? Well, it turns out that they all have to be absolutely undefinable. So again, this is like a very strong version of Tarski's undefinability of truth and satisfaction. So it's not that first order logic is weak to sort of see how standard satisfaction relates to the structure of a model. It shows that the structure of the satisfaction of those satisfaction predicates in no way is linked to the original structure. Those expansions exist, but they are all sort of, they live in their own world. They are set theoretically constructed. But, it's a longer story to give you all the details. Some of it happened quite recently. So I will just give you a brief list of things that were known in the past and what's happening now. So if you have a countable resplendent or recursively saturated model of PA, the following sets are absolutely undefinable. So this is something that my friend and my mentor, Henryk Kotlarski, and I were looking at in 1980s. And if you look at subsets of a model of arithmetic, and then you look at elementary extensions, all the kind of questions, what kind of subset of a model can be coded in an elementary extension? So we proved that all those sets must be absolutely undefinable using Kicker-Reyes lemma. And this had some extensions. There were some consequences about partial satisfaction classes. Those are those models of UTB that I mentioned before. But soon after that, Jim Schmerl noticed that the proofs here, well, the results were very far from being optimal. The optimal result about subsets of countable models of arithmetic is about undefinable classes. I have to tell you what a class of a model is. If you have a model of arithmetic and a subset of it, then we call it a class, or sometimes it's called piecewise coded. If for every element in the model, if you look at the initial segment below A, it's actually coded or definable in the model. Okay, and we call a subset of a model inductive if induction schema holds for all formulas in the extended language. That it's easy to prove. That's a simple exercise that all inductive sets are classes. And so it follows already from Schmel's result that all undefinable inductive sets are absolutely undefinable. And it's a beautiful argument. It's in our book that Professor Chang mentioned at the beginning. So many results follow from these things. But it's interesting from the point of view of your thinking about the philosophy of the subject, that somehow, it's a very natural thing to think about expansions of non-standard models, because in the standard model, every set is inductive. So if you want to have some natural expansions and you add more of a structure that you want the model to look more like the standard model, then you want to have the expansions to be inductive. And it turns out that it can be done. I mentioned last time there was a theorem of Stephen Simpson, how to add, using forcing in arithmetic, how to add new inductive sets to a model of arithmetic. But this result shows that you can do this. Yes, you can add those new sets. But again, they are very external to the original structure. You cannot see easily how to construct those models. You have to use some very non-effective methods to find those new sets. And then this is something about satisfaction classes. For a while, it was an open question. I discussed it with Bartosz Wcisło in Warsaw, who recently has done a lot of work on those axiomatic theories of truth. So here, this shows that all inductive models of axiomatic theories of truth are absolutely undefinable. But full satisfaction classes, the point about full satisfaction classes, they're kind of mysterious. You don't assume any induction about them. And there are interesting pathological satisfaction classes where induction axioms fail badly. And the question was, what about their definability? Are they absolutely undefinable or not? And we proved it, Bartosz, in kind of a more explicit way, and I proved it using some known results about automorphism and satisfaction classes, and that indeed all full satisfaction classes are also absolutely undefinable. And I just want to mention two more results, but this would be like a separate topic to talk about, that graphs of non-trivial automorphisms of recursively situated models are again all absolutely undefinable. This has something to do with Ehrenfeucht's lemma that I mentioned last week, for those of you who remember. And I find it again interesting because there is a whole big study of automorphisms of models of PA, of recursively saturated models, and the groups, the automorphism groups. And we have various constructions, various back and forth constructions. But again, this shows that no matter what you do, you cannot really find automorphisms of models of recursively saturated models easily. You cannot just look at some properties of addition, multiplication, and somehow build an automorphism out of that. They all come from non-trivial abstract model theoretic constructions. They do exist, there are continuum many, but they are absolutely undefinable. And I mentioned this result by Kikuchi and Hamkins on a slide just to be able to say this one more thing. I gave talks about this at our seminar. I want to remind you that we have this seminar on model theory of arithmetic called MOPA in New York. It's online. And Zachary Mackenzie was at my talk, and he then looked at the paper of Hamkins and Kikuchi and concluded that again, if you have that you have take one those inclusion reducts in a countable model of CFC, and if you look at possible epsilon relations that expand this reduct to a model of CFC, none of those membership relations is logically definable. They're all absolutely undefinable. Okay, so I see that maybe I went over everything a little bit too fast, because this is really the last slide I wanted to talk about. We could spend some more time on this or that, but maybe, it's certainly I covered a lot of ground. So maybe it's a good time for me to finish this and see if you have any questions that